All right, so in this last video, I'll show you all the examples from the previous videos, but now we will do them together in R. So I'll start with creating a new script, and then I'll call it, let's say, lecture 3.3. And then first of all, I need to load the people data. That will be my main data set in this case. Library read Excel, and then read Excel, and then people data. Okay, I will also turn it to data frame. Not necessary in this case, but it's nice to have a full control on what you have. And then of course it's always a good idea to check what you have loaded. So I will just look at these variables, and then you can see that indeed I got all the variables as numeric, and then you can see that this is the character, it's just the names of these people. So let me start with creating a simple multiple linear regression model. The first example that I have also in these videos, in this learning sequence, it's how income depends on three variables, on three predictors. It's age of person, region of person, and the sex, the biological sex. And then you can see that I will use the original values. Because I'm going to use different types of, I'm going also to center and to standardize at some point the data set. Let me create DO, meaning the original data, DO. It's just a copy of D. So I just make a copy. You can see it's a copy of D. And I will use DO when I don't need to standardize or to mean center anything. So let me create a model, a linear model, where income is a function of effect from age plus effect from sex plus effect from region. And then I tell R that this is the columns of data DO, data frame DO, and then I'll show you summary, summary M. Right. So that's exactly what you also saw in my video. So these are the estimated coefficients. You can see the intercept is not significant because we don't have any data points around intercept in this particular case. This is effect from age, how many euro per year in average you expect if year is getting up. And you can see it's a significant effect. Very unlikely this effect is actually observed by chance. Then we have a small effect and non-significant effect from biological sex. And then we have some effect from the region, right? Now let me show the regression coefficients. There are several ways to do that, but if you write coefficients, M, you can get the regression coefficients separately as simply as a vector. So B0, B1, B2, B3. And then also if you write B dollar coefficients, it will give you the same. So which way to use it's up to you. And then if you write conf int M, you will get the confidence interval. So this is 95% confidence intervals. And then if you want to get, for example, 99% confidence intervals, you just write conf, I think it's conf level, let me check, 0.99. Indeed, not indeed actually. Let me check it. I don't remember. Conf int. I just call for help, and then let's see. It's just level, not conf level, but just level. You can see here. So just level, and then you can see now indeed the intervals are wider than I had before. Right. Now let's make a plot where we show the regression coefficients as bars, and then the confidence interval as error bars. So first of all, I save the regression coefficients. So this is B and this is CI, confidence interval, so I save them. But I don't need the intercept, I don't need B0. So therefore I will make a little trick. I will say take everything but not the first variable, okay, not the first value. And then here I say not the first row, because you remember this is rows and this is columns. I need to exclude the first row here, and I need to exclude the first row, I'll show you, the first value here, right? So I don't need intercept. So let me run it, and then let me show you what I have in B. You can see only the slopes, the effects of the predictors, and then CI you can see also only the confidence intervals for the predictors, right? And then CI low will be the first row, right? So I just create a separate variable for that. So this is CI low. Sorry, I just need to fix this. Now you can see that this is CI low. It's just the first row. Oh, sorry, it's the first column, of course, first column, right? So let me show you again. You can see it's the first column, so it's a lower boundary of these confidence intervals. and then CI up, likely, I just say the second column, and then you can see it's an upper boundary. So now I have three vectors. Look, I have B, vector B. Now I go to console and then write it here. So let me clean it first. Vector B, three values. It's the estimates, right? It's what we have estimated, the lower boundary and the upper boundary. And now I can make simply error bar plot. So I have bars and error bars. So I write bar plot B, right? And this is the regression coefficients you can see. So I can, if necessary, I can also add, for example, the box, the grid, and so on, but I don't think it's necessary in this case, right? What I can show you, what I can also add is the error bars, right? So these are just bars, and I would like to add error bars. I use arrows for that, but I remember I need to keep the x variables, x coordinates of these bars. So middle of this bar, middle of this bar, middle of this bar. This is how to do it. I simply ask bar plot to return something, and when I ask bar plot to return something, bar plot returns, this function returns exactly the position of middle of the midpoints of every bar. Now I can use these positions to make the plot. This is the upper part of the interval, angle equal to 90. And then you can see now we have a little problem, right? So we don't see it because the limits are not good enough. Of course, I can change the limits here. This is the bar plot. I can change the y limits manually, but let me make it automatically because I already know that this is the lowest possible value, this is the largest possible value. So what I can do, I can simply write y limits goes from the lowest possible value, Ci low, but I need to take a minimum of these three values, right? And the maximum possible value, Ci up, and also the maximum of this, right? And then I simply run it again, and now you can see that all the bars are fitted well, right? Now I can also add the lower boundary. So in this case, I just simply change this to low. And now you can see all error bars similar to what you have seen before. You can also change, for example, the color and everything, but let me keep the default colors just to make it a little bit faster, right? And then you can see that, for example, this is positive and this is the uncertainty negative. This is crosses 0, so there is no significance influence. It can be positive, it can be negative. We don't see evidence that sex has any influence here. And then the region is negative, and that's the confidence interval of the region, right? Regardless how many predictors I have, this plot always will look like this. So let me make it a function. So let me make a versatile function. Let me call it plot coefs, right? It's a function. It's a function which has only one argument. It's the model, okay? You can also add an argument, the confidence level, but I don't think it's necessary in this case. So let me just remove confidence level. It will be always 95%. If you want, you can make it, you can change it later. This is the body of the function. And now I simply move all these things inside the function, right? And then I need to load this function to my environment. So I run this code, and then you can see that I have this function plot coefs here. And now look, let me clean it. Yes. And then I will just write plot coefs m, and then I got this plot. So now I have a versatile plot which I will reuse in this video for the other models. Okay, so you can of course improve it later inside this function, make some nice colors, also make perhaps better access and so on and so forth. But let's keep it as simple as possible. Okay, so these are regression coefficients. Now how to make predictions. Well, strictly speaking, if you want to get the predicted value and, for example, make also plots for errors, cuckoo plot for error, we will do it in a minute, you simply take $m fitted values. So that's one of the cases, one of the ways to do it. So you can see all these predicted values are here. So for example, I can save it to yp, to variable yp. I can also save y as a separate variable, which is $income. It's my original y values, right? Now I can compute error as simply a difference between y and yp. And then, for example, not e, but y and yp. And then, for example, make these plots that we made before. For example, plot y and yp. It's the predicted versus measured plot, right? So this is the plot, and then I can add a line, a equal to 1, b equal to 0, right? So this is the other way around. Never remember this. Right. So this is the ideal line, and these are the predicted values. Also can add a grid, for example, right? So this is the grid. So now you can see how predicted and measured values, let me make it square it like this, and measured values support each other, right? So how they close to each other, so to speak. So this is the ideal line. And then you can see indeed it's much better than, for example, what we had in case of the simple univariate regression, right? The simple linear regression. And then it's always a good idea to have the same limits here. So I will say, I will make the limits first, limits equal to C. And then look what I'm going to do. I'm going to do the following. Mean C, Y, and YP. It means take a minimum of these two vectors, right? And then max C, Y, and YP, right? Again, I try to make it versatile, so it will work for anything. And then I say x lim equal to lim and y lim equal to lim. So let me calculate the limits first. So these are the limits. You can see this is the smallest value I have in both vectors. This is the largest value I have in both vectors, right? And then now you can see that the limits are the same, and then everything else is also quite easy. Again, I can make it a function. I can call it, for example, plot predictions, right? In the simplest case, this function should get two values, y and yp. Of course, again, you can make it more nicer if you add some titles, x labels, and so on and so forth. But in the simplest case, it should be like this, right? And then after that, you simply do it like this. Again, run it. And then you will see, let me see what I did wrong. I think I made something wrong. Probably forgot the plot predictions function. So this is the mistake. Now let me run it again. Now you can see you have two functions here. And then you can simply write again plot predictions and then y and yp. And then let me clean it. And then let's see if it works. Yes, it does. Right. So again, it's versatile, so you can reuse it later. Okay. If you look at the M, what is inside M, you can see it has a lot of things, right? It has a lot of things. And the good thing is that you can see it has coefficients, it has residuals, it has effects, fitted values, a lot of different things. Some of the things we didn't even discuss in our course, right? But you can see that it also has the original data values, the income, right? You just need to know that the variable is income here, right? So strictly what you can do, you can actually extract the y values from the model. So instead of taking y and yp here, you can provide model and extract this y values from the model. But we will keep it simple, so let's keep it like this. Okay. Now I can also make a plot for residuals. In this case, I will just write plot E, YP, and E. You remember the randomness of residuals. So this is the, not Y, but E. So this is how random the residuals are. And then I can also add a line. In this case, it's a horizontal line that shows the error equal to 0. Again, you can see a pretty random, right? And then finally, what I can do, I can also make a cuckoo norm plot for residuals. And then cuckoo line plot for residuals. And again, you can see that the residuals look pretty good. And what now I can actually do, I can combine all these plots together. MF row equal to C22. And then you can see that I will combine the predictions here as well. And then also the regression coefficients. So I will just copy this. So I make a figure with 4 plots, the 4 main plots, the observation of the predictions, right? So you can see the regression coefficients, the predicted versus measured plot, the error plot depending on YP, so this should be random, and then the QQ, quantile normal probability plot for the residuals, right? So this is kind of an overview of your model. So these are 4 main plots that you can make, okay? Of course, again, you can make them much better. You can add different labels, different titles, and so on, but sometimes the simpler the better. Good. Now, the next is how to get predictions for new data points. Well, imagine that we have a new data point. For example, it's a female person from Scandinavia whose age is 50 years old. What's the income we expect for this person? So in this case, you write yp equal to predict, then you take your model, and then you need to provide predictors as a data frame. Also, it will be just one row data frame. So you say data frame, and then use the same names for predictors as you have them in your formula. So you can see that in my formula, I have age, sex, and region. So I should use the same name, absolutely the same name. So let me say it, age equal to 50, region Scandinavia, it's -1, and then sex is 1, it's a female person, right? And now you can see that the predicted income of this person is 43,000 euro, approximately 43,000 euro per year. Of course, it's based on the sample that we have. So this is how to make predictions. Okay, so now let's talk about how to do the same, but for standardized data. Let me show you the example that I showed you before, box plot, for example, D, and then I need to select the variables that I want to make the box plot for. Let me just do it. Let me just do it for all of them. Okay, so except names, so -1. It means don't use names, right? And then let me also make it horizontal equal to true, right? So this is the case. You remember that in my videos I didn't show you the income. You can see income varies much larger than all the other variables. So let me remove the income also from here. It's variable number 7, if I remember correctly. Yes, indeed. So these are, let me get back to layout with one plot only. MF row equal to C11. You can see that indeed they vary quite a lot. Strictly speaking, I'm not allowed to make this plot because I have different units for every variable here. So this plot makes no sense. It's just for the visualization purposes. If I want to have these variables sharing the same variable space, of course I need to standardize them. But you know that I cannot standardize the qualitative variables. I mean, I can mathematically, but it would make no sense. But let's do the trick that I showed you also before. So for example, if you take sex values, right? So you can see they are either -1 or +1. If you add 1 to these values, they will be either 0 and 2, right? And if you divide to 2, then you will turn them to dummy variable, which is just a switcher, right? On and off. Is female or not female, right? So in this case. And then let me do the following. Let me create a new data set, DS, meaning de-standardized. I will say that it's a copy of D. So it's a copy of original dataset. So it's just not to spoil the original dataset. And then I will just simply say like this, ds$6 equal to, and then I will dummify this, right? And then if you look at ds inside, you can see that now sex is dummified. So it's 0 and 1. It's not -1 and +1 anymore. Now I can do the same trick for the region, So ds region, ds region +1 and divided to 2. We do it only because the original dataset is coded by -1 and +1. Otherwise, of course, the dummification is easy if it's just a qualitative variable, right? So again, it's +1 and -1, but age has to be standardized. And let me compute average age and average standard deviation. First, I will use this later. MA equal to mean of ds$h, right? And then SA equal to a standard deviation of ds$h. And then I standardize this variable. So I say ds$h. Let me show you the values first. Then I say subtract average. So let me run it all. So I first mean center. So this is now, it's not the age, but it's a distance, how far this particular age is from the average, right? And then I divide it to standard deviation. So now these values are standard deviations. For example, age of the first person is by 1.4 standard deviations larger than the mean. And let me keep it back to the age variable, in this case, right? So now the values are standardized, and now let me just make the same model, but with this new data set. So the model will be the same. It will be income depends on age plus sex plus region, right? But data set, now it's a standardized data set. And then if you look at the summary, you can see now that, first of all, intercept is significant. You remember what is intercept in this case? It's a salary of a person who has average age, right? So it means this will be 0, but you remember it's a z-score now. Z-score is 0 when you have average age. sex is 0, it means it was -1 before, right? So it means it's a male person. And then the region also 0, it was -1 before, it means it's a Scandinavian. So Scandinavian, this is it, right? So, and then I can also make these predictions like I did before, YP, predict, right? And then let me make predictions for the same person, right? Data frame. Well, first of all, h equal to 50, but now I cannot write 50. I need to turn this into standard deviations, right? So I should write 50 minus MA divided to SD. That's why I actually keep SA, keep all these variables before. So now I need to turn it to standard deviations first. That's the drawback of this approach, right? And then the second, it's sex is now, you remember it was a female, right? The order doesn't matter. It was a female, it was 1, and here it's also 1, but region, it will be 0, because now it's not -1, it's 0, right? And then if you look at the predicted value, you can see it's the same value. It's absolutely identical. So let me show you let me just run it here. So you can see both, let me call it YP1 and YP2, right? Then I run everything, but now I have them separately, right? See, YP1, YP2, then we can see they are identical. So the model didn't change. Moreover, if you look at the summary of this model, of course, regression coefficients now look different, but all the statistics, everything is the same. Okay. Now let's make a plot. Let me just simply copy all these lines, and then paste them here. I will also need to copy some other things, right? So I also need to copy the way I created E, Y, and YP, these three. And I need to paste them just before. I could also make a function, of course, but in this case, I didn't do that, right? Here we go. So now you can see that what is different. This plot is the same. This plot is the same, and this plot is the same. But what is different is this one. So now you have, this is the variables show you the effect per standard deviation. And that's why, for example, H and region are now comparable, and also the variation, the uncertainties are comparable, because now it's uncertainty per standard deviation. And then you can see that also the uncertainty for sex is comparable, right? But now you can see it's very small. I mean, it's crossing 0, right? So it's not significant, like we also discussed before. Okay. Finally, as I said, you can skip the standardization. You can, let me just copy this. And then you can use only mean centering. In this case, what you need to do, let me again make a new data set, DM, mean center it, it's a copy of D. And then I still compute the average of H, but I don't need to compute standard deviation. So I remove this. So that will be DM, and this is it, right? So, and then I still need to dummify the variable. So I will just copy and paste the dummification part. This is 2. So I will paste them this time under the mean centering. Okay, just need to change DS to DM. Okay, so here we go. So now we make a new data frame, DM, which will contain all the same as DS, but now the H in DM is not standardized. It's only mean centered. So you can see that now the H has real distances in years from mean, right? And then if I run the model here, you can see again, we still have the same t values, the same p values for all the regression coefficients, but what is different is estimated, because now it affects, this effect is per 1 year, not per 1 standard deviation. And if I want to use this model, I also need to change this. So now I don't need to divide to standard deviation. I need just to mean center the H, right? And then you can see that if I run it again, you can see all the predicted values are the same. So that was about how to create models and how to investigate the performance of your models. And now let's talk about how to visualize the models, the contour plots and the surfaces. However, as far as I can see, this video is already long enough, almost half an hour, so I will stop now and then discuss these topics in the next video.